Okay, guys. All right, guys, we're back. We have sound today. Hopefully, this is working. Um, Yesterday, we learned with the second part of the fundamental theorem of calculus how to find the derivative of a function that's defined as a definite integral. And remember the little pattern that we had for that? How did that go for the sake of anyone that's not here? What do you do first? Yeah, if you have to get the derivative. Well, no, not if you like. Okay, technically, you could rewrite f of x without the definite integral. You could take the antiderivative and plug in upper and lower and subtract. Yeah, and then take the derivative. But we learned a quick way to find the derivative. Remember that? No, Tim, what were you gonna say? No, you gotta start with something else. What's up to get the derivative? What do you do first? You take the derivative of the upper limit of integration, and then what do? Plug in the upper limit of integration for all the t's, right? And you multiply them together. Then what? Minus derivative of the lower limit of integration times what you get when you plug the lower limit of integration in for t. So go ahead, do that now. Check the homework. Okay, let's see how you did. I can't wait. Okay, now you should have the derivative is cosine x, because that's the derivative of the upper. First, times the quantity sine x plus square root of sine x minus 1. So derivative of upper, plug in upper. Minus, I think I am recording. Yeah, square root of x squared. Is that what you're saying? Yeah, technically, I think maybe I should have left it the square root of x squared, because the square root of x squared really only equals x if x is a positive number. Think about it. Like the square root of negative 3 squared is 3. It's not negative 3. Like that. So derivative of upper, we plug in the upper, minus the derivative of the lower limit of integration, so that's your 2x, and then you multiply that by what you get when you plug in the x squared. What do we do? Good. All right. Okay. So we gotta check the homework. So let's see. Now I have it all broken up. I know number one, a lot of people had trouble with for some reason. What was the deal with that? People didn't get 3 right because they had 3x squared over x cubed. But that's the same thing. Number 3. So sometimes my answers are reduced. Like number 5, you probably have a 2 over 2x plus 2 for the first term. Don't mark that wrong. Don't mark it wrong. It's just not simplified. No, but you have to recognize when your answer is the same. You got to recognize it. It's equal. Yay. Okay, ready? Wait, what was the problem? Good? All right. Okay, looking at 7 through 11. 7 through 11. Yeah, nice. That doesn't happen every day. Yeah. Yes. Yep, chicken. Yep. You probably have 4 times negative sign over, same thing, right? All right, you ready? Let's do this. What? We didn't. We couldn't. Okay. 4 times negative sign x. Here you go. See, look, the streak's broken. Okay. No, it had to end. Fourteen. 12. 14. Yep. 15. Okay, you ready? We're gonna go over some. You saw the answers. Um. Okay, number 12. Actually, let me just put up a blank page here. 12, they ask you to write the equation of a tangent line to a function at x equals 2. Right? When we write the equation of a tangent line at x equals 2, how do y minus y1, how do you get y1? What do you plug 2 into? The function or the derivative? You got two choices. The function, right? And then that equals the slope. How do you get the slope? You plug 2 into the derivative. And then what's the rest of it? X minus 2. This is just the point slope form. It's how we write the equation of a line, but when that line is a tangent line, well, when the line is any line, y1 you get by plugging the x value into the function. But when it's a tangent line, you get the slope by plugging the x value into the derivative. So, we got to get f of 2. Yay! All right, so for f of 2, the y1 value, remember guys, in this one they told you that to get f of x, it's the definite integral from 2 to x of the cube root of t cubed plus 1 dt. That's how the function's defined. So how would I get f of 2? Plug the 2 in, so it'd be the definite integral from 2 to, well, f of x is equal to the definite integral from 2 to x. To get f of 2, from 2 to 2. I don't care what that function is. Okay, again, because to get f of x, it's the definite integral from 2 to x. All right, this is how they define the function. So if you want to get f of 2, so you're putting 2 in for x on this side, you have to put 2 into the x on the other side. And what is the definite integral of any function from 2 to 2? 0. So our y1 value equals 0. So far I have y minus 0. Now we got to get the slope. We have to get the derivative at 2. So let's get the derivative. Put this over. Oh, no. That's all right. I can handle that. All right. Sorry, there goes all the color. Now it's just making things confusing. So yeah, this goes here. Anything else? This goes up there. Beautiful. Okay. So what is f prime of x equal to? This is f of x. Second FTC. If your function is a definite integral from 2 to x with the square root of t cubed minus plus 1, what's that prime? Yeah. Square root of x cubed plus 1. Right? Derivative of upper is just 1, and you plug in the upper. So that's what you get, because the derivative of the lower is just 0. So now we just have to plug 2 into the derivative to get the slope of the tangent. So f prime of 2 equals the square root of 2 cubed plus 1. Square root of 9 equals 3. So this is 3. So the equation of our tangent line is y minus 0 equals 3 times 20x minus 2. You can distribute the 3x minus 6. That was 12. That was a good one. Was it 14, the next one I heard? Okay, 14. Oh, wait, that's not the one I was thinking of. That's 14. Okay, well, we're going to apply the second fundamental theorem of calculus. When you want to find the derivative, that's what this means out here, of a definite integral, you take derivative of the upper, h prime of x, times what you get when you plug that upper limit in for t. So it'll be g of h of x. 14. That's just like what we were doing, but then where is that? H prime of post choice B. They just switched the order. And then we had, what was the next one, guys? 15. 15 was kind of neat. 15, so they give you one of these. F of x is equal to the definite integral from 1 to x of sine rad t dt. And then they ask all these questions, and I can tell from the choices that they must have used a calculator. See those numbers? And they're talking about where's the function increasing or decreasing. So if you want to know where a function's increasing or decreasing, what do you got to get? The derivative, right? So what would the derivative of this function be? Sine rad x. And they're talking, so what we want to do is they're talking about on the interval from 1 to 5. I want to see this derivative on the interval from 1 to 5. Just make sure you're in radian mode in this class always. In this class. So you want to actually look at this derivative, and the big thing is that you set your x min equal to 1 and your x max equal to 5, because you want to look at it on the interval from 1 to 5. So after you enter the function, make sure you're in radian mode. Window, the x's have to go from 1 to 5. And when you look at the graph, there's the derivative. What can you tell me about this derivative for values of x between 1 and 5? Well, it goes up and down, okay, but what else can you tell me about it? It's positive. If the derivative is positive for all values of x between 1 and 5, what is the function doing? It's increasing. That was fun. So it's choice C. Yeah? Does that make sense? Really, wake up. Sure. Go on. You were going there for a while. Really? I know, but I know that. Glazed over. Was there anything else in the homework that you wanted to see? So that was 15. I mean, 16, if you didn't get it right, it's probably because you didn't reduce it. Like for 16, you probably got that for an answer. And then you just remember, when you divide by a fraction, keep what's up here and then flip, and one of these x's is going to cancel. So it'll just be negative 1 over x cosine of 1 over x. So one of the x's will cancel. All right, ready to move on to today's stuff? Yeah? Good. Okay, so what you should see on the first page of your notes is this question. What does the definite integral of the derivative represent? And I think it might be easier for you, instead of leaving it written as dy dx, I think I'm going to write it as f prime of x. So let's just look at the definite integral from a to b of f prime of x. What does that mean when you take the definite integral of the derivative of a function from a to b? Okay, first thing you would do, you get the antiderivative, which would be f of x. Now we're not done because it's a definite integral. We have to evaluate that from a to b. Then what would we do? Okay, so f of b minus f of a. when you integrate, when you take the definite integral of the derivative of a function, it gives you the change in the y values of the function. It gives you the change, total change in the function from x equals a to x equals b. Now, slope you need over the change of x's. So it gives you, it's the change. Sometimes people say the total change or the net change. That's what the name of our note says, net change. So I'll just write the total change in the function, in the y values of the function. From x equals a to x equals b. What you're doing is like you're summing up all the infinitely small changes to get the total change. And I'm going to illustrate this with a little graph because I'm not sure how far that's looking. Just to illustrate this, let's graph the parabola y equals x squared just on the interval from 0 to 5. We don't need to see it over here. Bless you. So just graph the parabola y equals x squared from 0 to 5. Something, rough sketch. From x equals 0 to x equals 5. Right, and the y coordinate here would be 25. So just to have like a real function to talk about, let's get the derivative of that function. So what would the derivative of this particular function be? 2x. And let's say I want to take the definite integral of the derivative from 2 to 5. I'm just picking the two randomly. I just wanted to have the whole graph here, but this part of the graph. If I want to take the definite integral of the derivative of the function, in this case, the derivative we said would be 2x, right? And 2 to 5. Now I know I'm kind of going forwards and backwards here, but I just want to show you what happens when you take the derivative, the definite integral of the derivative of a function. What's the first thing you would do? You would integrate. What would you get? X squared, right? We'll go from 2 to 5. I know, what's the point? I'm going backwards because I'm trying to get you to see an example. I'll show you in a second. I think it'll be clear in a couple minutes, or else I fail. We'll plug in the upper limit, the lower limit, and subtract, right? So I would have 5 squared minus 2 squared, which is what, by the way? 25 minus 4, so that's just going to be 21. Because all I'm doing is I'm taking f of 5 and I'm subtracting f of 2. Okay? Let's see what this means graphically. So when you integrate the derivative of this function from 2 to 5, you're going to get 21. Okay? What I'm saying is that's the change in the y coordinates from x equals 2 to x equals 5. Well, let's see if that works. When x equals 2, what is the y coordinate on our parabola? 4, right? And we said when x equals 5, the y coordinate's 25. What's the difference between these two y coordinates? 21, right? The change of y's in along the function, okay, from x equals 2 to x equals 5 is 21. Okay, so another way to get the change of y coordinates along a function is to integrate the derivative from this first x to the last x. Look at the total change in the y value. The function. Huh? See it? Okay. Remember the first fundamental theorem of calculus basically told us if you want to find the definite integral of a function from a to b, you first take the antiderivative of f, which is uppercase f, and you plug in the upper and lower and subtract. It taught us how to find the definite integral of a function. So we always thought of it, well, f, capital F, is the antiderivative of lowercase f. But that also means, what about f? What's its relationship to capital F? If capital F is the antiderivative, what's F? That's just the derivative, right, of the upper. So this is saying what we're talking about today, that when you take the definite integral of the derivative of a function, you get the change in functional values. All right, it's just instead of calling this f prime and that f, we're calling this lowercase f and not uppercase f. Well, if we start with this, we can solve for f of b. How would we get f of b all by itself? How would we solve for it? Add f of a. If we add f of a, we'll have this, right? If we bring the f of a, add it over here. And then tell me what I would do to go from this line to what's boxed in here. What are we doing? Go from here to here. The kids at home. So we said we add f of a to both sides. Now we're here. The kids at home are right here. And now what do we do to go from this line to this line? Did I forget the dx? Whoa. Oh, that's bad. Oh, okay. All right. Assuming that was there. Switch sides. We're just switching sides. Right? Yeah, okay. Now this is going to help us. This is what this is saying. Suppose you want the y-coordinate on the graph at some value x equals b. So you want that y-coordinate. Well, if you know the y-coordinate at a, you know f of a, you can start with f of a and add the change in y. And how do you get the change in y? You integrate the derivative from a to b. This comes up on the AP exam quite often, this concept. So if you want to get the y-coordinate at b, take the y-coordinate at a and add the change in y. To get the change of y, you integrate the derivative of the function from a to b. And when you do this, just make sure that whatever this x value is in here, it's the lower limit down here. We're going to have fun with this one, I think. And I thought, because Tim was saying he'd like to get back and do some motion problems, I said, okay, let's do that. You know what? He said I missed the motion problems. Remember that the velocity is the derivative of the position function? Good times. So if you take the definite integral of the velocity, now the velocity is ds dt. It's the derivative of position function. What am I going to get? Like, what is this number going to mean? If you take the definite integral of velocity, so you take the definite integral of the derivative of position, think about what happens when you take the definite integral of the derivative of a function. What do you actually get? Okay, you get the function. So if you integrated that, you would get the function, but then you'd have to still plug in the b and the a and subtract, right? So you get the position at time b minus the position at time a. You get the change in position. When you integrate the derivative of the position function from a to b, you get the change in the position from a to b. You get the total. Remember what that word is? It's not distance. It's displacement. Final position minus starting position. You integrate the derivative of position, you get the change in position. All right, let's try to see it with an actual example here. Let's graph this particular exciting velocity function. Velocity is a function of time, so let's just first set this up. So on the y-axis, that's going to be our velocity, v of t. And on the horizontal axis, that'll be our time. We're going to measure time in hours. So I'll just put little hours here. And the velocity, we're going to measure that in miles per hour. What's miles per hour? Is that really, you're kind of used to that in your life. It's not an F, miles per hour. Not like I'm making up weird units or something. Okay, now we want to graph the velocity function v of t equals 50. Constant function. Nice. What is that graph going to look like? horizontal line. So let me just put a little 50 here. And here's the graph of our velocity function right there. Nice. Now, the first question we're asked here is find the definite integral of our velocity function from time 3 to time 7. Right? Two ways we can do it. Probably the most straightforward way to do it is just plug in the velocity function. So in other words, take the definite integral from 3 to 7 of 50. I mean, for v of t, I just put in the 50. So we could take the antiderivative of 50 with respect to t. What would that be? 50t, right? And we could plug in the 7, plug in the 3, and subtract. So what's 50 times 7? 350. Then we could plug in the 3, so minus 150. And what would we get? 200, right? All right, I still don't know what it represents, but I could get that number. Now, another way I could get that 200, remember the definite integral in area? When you find the definite integral of a function from a to b, it has something to do with area. It's the area above the x-axis minus any area below the x-axis. Okay? Well, this graph is all above the x-axis or t-axis. So if I want to find the definite integral of 50, and I've got a graph of 50 from 3 to 7, 3 to 7, I could just find the area of that rectangle. Area above minus area below. So it's all above. So it's a rectangle. So from 3 to 7, that's 4. So that takes 4 hours. And I'd multiply it by the other dimension of our rectangle, 50. So if we take 4, let's think about this. So I have 4 hours, this is the 1, right? I'm multiplying, times 50 miles per hour. I get 200, right? But I want you to see that units follow operations. Whatever you do with the numbers, the units go along for the ride. So if you multiply hours times miles per hour, you get miles. So yeah, you get the 200, but I think it's helpful to see, because you're getting area, you're going to multiply, okay? So the units are miles. So it's every time you want to get the units of an antiderivative, you're going to multiply the units of the integrand by the units of what we call the differential. You multiply units. Right? Units follow, they do whatever the other operations are doing. Oh, you do. So you are multiplying them. You're crossing out, you're canceling a numerator and denominator. Yeah. What? So when we found the definite integral of the velocity, which remember is the derivative of the position function from time 3 to 7, we got 200 miles. What is that, though? Like, what's 200 miles? Say change again. The change in the position from what time to what time? From 3 to 7. We just figured out, so if you integrate the derivative of the position from time 3 to time 7, that number is the total change in the position. Okay, when you integrate the derivative of position, because that's what velocity is, from time 3 to time 7, you get the total change in the position from time 3 to time 7. You get position at time 7 minus position at time 3. So, right now, we don't know what, up to this point, we don't know what the position is. We just know how much it changed by from time 3 to 7. We know it changed by positive 200 miles. Okay? What easy way? Well, this is easy both ways, right? Integrating, you can use a graph if you can calculate the area, or you can just get the antiderivative and apply the FTC. But now comes the fun part. Suppose I told you at time 3, its position was 70. In other words, it was on this giant number line, and at time t equals 3, it was at 70 on the number line. Okay? Telling you where it was at time 3. It's like giving its position. And now I ask you, what's its position when t equals 7? We know where it was at time 3. It was at 70. Where is it now at time 7? 270, right? The position at time 7 is equal to its position at time 3 plus the change in position from time 3 to 7. Remember we integrated the velocity, ds dt? The position at time 3 is 70 plus 200. We get 270. That's its position at time 7. So we knew as long as you're given a position at a particular time and you're given the derivative of position, you integrate the derivative to get the change in that function. You know where it was, you know how much it changed by, you can get what it is. This comes up a lot on the AP exams. It's important. So let's try another one. It's that important, we're doing another one. Woo. So now let's say I want to know, where is this thing when t equals 10? What's its position at t equals 10? I have 2 points I could start at. I could start at 3 or 7. You want to start at at 7? So if I want to know the position at... No, I'm connected. Okay. So if we want to know its position at time 10, we can take its position at time 7. We know that, right? Guys, if we want to know its position at time 10, take a position you know at time 7. We just figured out that was 270, right? Plus, what would I write for the change in position? You'd integrate from 7 to 10, plus the definite integral from 7 to 10 of the derivative of the position, which is just the velocity. I'm writing as ds dt. It's just the velocity. Now, I think we should get that the quick way from the graph. I mean, we could fill in the 50, take the antiderivative, or we could just look at the graph of the velocity. What's the definite integral from 7 to 10 of the velocity? 3 times 50 is 150. Okay? So 270 plus 150 equals 420. Last one, because I want to show you it doesn't matter whether you're going to the right or left. It always works the same. Let's say we want to figure out the position when t equals 1. We could take the position, let's go back to time 3. All right? And we have to add the change. Now, this is the big thing when you're doing this. This number in here has to be your lower limit if you're saying plus the change. So it has to be from 3 to 1. Then, yeah, if you want to use the graph to get the definite integral, the lower limit has to be less than the upper limit. So you could rewrite it as minus the definite integral from 1 to 3. If you didn't want to use the graph to get the definite integral, it wouldn't matter which was lower or higher. So, yeah, so 70 minus 100 equals negative 30. With the word problems, like the first one, okay, that you're going to have for homework, they give you the rate of change. That's the derivative. So if you look at the first question, they tell you that the value of the house at time zero, what was it, 220,000 or something? 225,000. Then they give you the rate at which the value changes. That's like your DVT, change in value. Can you just remind me what that was? 201? Okay. This is your value at time zero. This is the change in value over change of time. The reason you know that is because this is in dollars per year. So if you want to know the value of the house at 10 years, you take the value at time zero and add the change in value from 0 to 10. Okay, so you have to integrate what's above this. I just don't have a chance to write that. You can do these on the calculator. Okay?